So the final circuit element we want to look at how to transform to the S domain is our capacitor. And so our approach is going to be the same as we saw with the other two elements. We want to take the Laplace transform of the IV equation. And so the current voltage equation that we want to focus on is that our capacitor current I of t is equal to C times dV of t dt. So we're going to take the Laplace transform of this. On the left side, we have our current becomes capital I of S. And again, we're going to be using our time differentiation property on the right side. So time differentiation property from our Laplace tables. And our C is a constant, so it just comes along. And our time differentiation property says dV dt becomes S times capital V of S minus lowercase v of 0 minus. So similar to what we saw with the inductor, our capital V of S is our Laplace transform of lowercase v of t, and our lowercase v at 0 minus is a time domain value. So multiplying that that C through, we can see that our I of S is equal to SC times V of S minus C times our lowercase v of 0 minus. And so again, like we saw with our inductor, this second term, the C of V 0 minus, is going to represent our initial conditions on our capacitor. So we could also solve for our voltage instead. So if we take this equation and we solve for V of S, we'll get another form, which is V of S is equal to 1 over SC times I of S plus lowercase v of 0 minus divided by S. So similar to what we saw with the inductor, we're going to have two forms, and what we'll see in a minute is that's going to translate to two circuits which we can choose from depending on our particular circuit and what we're trying to find. Okay, so let's look first then at our time domain. So our time domain, we have some capacitor with capacitance C, and we have some voltage across that capacitance, which is lowercase v of t, some current flowing through that capacitance or capacitor, which is I of t, and we'll also have some initial voltage on our capacitor. So let me move this over here. C, we'll have some initial voltage on our capacitor, which is lowercase v of 0 minus, but our capacitor voltage has to be continuous. So capacitor voltage is continuous. And so what that means is it can't change instantly. So if we have some value at 0 minus, it's going to equal the same value at 0 plus. And more generally, we can just say that's the capacitor voltage at t equals 0. Okay, so that's our time domain circuit. So what we want to look at now are the two different S-domain representations we can have. So we can have an S-domain representation with the voltage source and an S-domain representation with the current source. So let's look at each of those. So first, let's look at our representation with the voltage source. So voltage source. So let me draw it, and then we'll relate it back to our equation above. So we have a capacitor, and it's going to be in series with the voltage source. And so the voltage source is going to represent our initial condition. So really, the voltage over here between these two terminals is our voltage across the capacitor. So this is going to be V of S. Our capacitor, okay, so we're going to have some current. Let me label that as well. We're going to have some current I of S. And so let's bring down our equations, same as we did last time. Okay, so let's put this one here. And then we can move our voltage one over here. Okay. So with our voltage equation here, what we can see is that this voltage V of S is equal to our current times 1 over SC, so that's telling us our impedance of this capacitor is going to be 1 over SC, plus some voltage V of 0 minus over S. So because we're adding that voltage, the polarity is going to be on the top, and we're going to have V of 0, and we can have 0 minus 0 plus. They're both the same, so let's just call it V at 0, divided by S. So that's what our S-domain circuit with a voltage source would look like. So now we also have this other representation where we can use a current source. So let me draw that out. So we're going to have our capacitor in parallel with some current source. And so again, the current source is just representing the initial conditions. So between these two terminals, we have our voltage V of S, and out of these terminals, or coming into our combination of our capacitor and our current source, we have the overall current I of S. And so what we can see from this equation here, if we consider KCL, we see we have a current in the middle branch and a current in the right branch. So in the middle branch, it's V over an impedance of SC. Well, so V over 1 over SC. So we get something that looks like this, and that SC comes up to the numerator. So that means this impedance here is going to be 1 over SC, the same as it is for our representation with our voltage source. And now we see we're adding this second term here, or rather we're subtracting it, which means that our current direction is going to be going up. And so the value of that current is going to be C times V, lowercase v of 0. Again, because remember, capacitor voltage is continuous. Okay, so again, like with our inductor, we need to keep in mind that these terms, and also then this voltage source and this current source, represent our initial conditions. And so our initial conditions for a capacitor is going to be voltage, but you might also see that reported as initial capacitor energy, and so we can relate that from our energy in the capacitor is equal to 1/2 CV squared. So that's how we can relate energy to voltage in a capacitor. So again, why do we need two forms? It turns out in some cases it's going to be more convenient to use one form over another, and it just depends on what we're looking for and how the circuit that the capacitor is in is arranged. And so we'll see that in some of the following examples. But basically we want to choose one that's going to make our analysis a little easier. That doesn't necessarily mean we have to choose one and there's only one right choice. It's just oftentimes one's going to be a little bit easier. So let's quickly talk about our capacitor impedance in this S domain. So our capacitor impedance in the S domain, and so similar to our inductor, this is defined for 0 initial conditions. Okay, so 0 initial conditions, so we have 0 initial voltage on our capacitor. And so with that in mind, these terms circled in green are going to go away. And so from either equation above, we can then see that our capacitor impedance in our S domain is equal to V of S divided by I of S, which is equal to 1 over SC. So now that we know how to convert each of our 3 passive elements to the S domain, in the following videos, we're going to spend a lot of time looking at different examples and seeing how we can step through this whole process of doing our Laplace analysis.